Okay. Can you hear me? Yes. Can you hear me? Okay. Good. So I haven't seen you guys for a week, so I hope you have a good holiday. Before we get start, let's quickly review what we have. Oh, not there yet. Sorry. Let's quickly talk about our main thing because we're waiting for the projector to be on. So first, remember your homework 2 with you on, I think, next Friday. Good. So it's on topic 2. And the other thing is I think I asked for the time for the final text for this class, and where I said is majority of you have chosen for 4:30 to 5:30. So we are trying to ask if anyone is not feasible, let the TA know, and then we try to see what can we do for you. Otherwise, if no one have said anything, then we assume everyone is okay, and then we'll proceed with the timing that I announce it. Okay, so I guess we can just quickly start now. Just to quickly remind what we have done. Random variable is the way you put numbers to outcomes, right? So and you only do it only if it's meaningful, right? If you put number is a good way to present what we want, that's the case, right? It's just like some measure. You can treat it as a measurement, right? Just like the things that you care about, the outcome can be summarized by a number, right? Then it's a random variable, right? Of course, here we focus on, we omitted, it's called univariate random variable, means only a single number can represent what we want, right? In some other cases, you actually need more than one number, right? And that would be what we call multivariate setting, which is not the concern for us. We implicitly use it, but we don't talk about those, but the idea is very similar. And depends on what we can assign a number to present a random variable. If this is a discrete, it's a natural numbers, then there's a discrete. If we try to assign decimal numbers or real numbers, then it's called continuous. And for discrete and continuous, there are the distinction is because of the way that we use the math tools. For discrete, you can use your high school tools, but for continuous, because it's involve infinity, it requires some idea of limit that naturally goes to talk about integration or differentiation, which we don't assume you to have knowledge on those, okay? But so that's why we talk about discrete in greater details, where everything actually the intuition will carry through to continuous, but for calculation we just skip those calculations. And we have give you example how you call discrete number of head, number of tail for a tossing a coin once or twice and so forth. Continuous, you have a stock or a temperature, right? For discrete, we learn the way we can describe a discrete is got the big P and the big F, right? The big P is you give me the value, any number there, I give you the probability, right? So and the big F, the cumulative one, is the one that you add up all the P's, right? That's what it's supposed to mean. And for discrete, I mean, the two of them are similar or actually the same thing, but this different way to write the thing. And the P is sufficient, right? It's most natural one, right? Because this is exactly probability, but the F1 is still very natural because it is adding all the thing below, right? And probably some of you may ask, and also read the textbook would ask, okay, we talk about this one, right? Is it why no one talk about this guy? Okay, no one talk about this guy, right? Or this guy, or this guy, right? Depends on which one you care. And indeed, they do have have names, and actually this is a very famous function in, if you study influence or actuarial science, that's called the survival function, which is 1 minus f, they call S, survival S. Okay. And because they are the same thing, so we don't talk about those. Okay. It's just like, but because survival means that, say, what is the likelihood that this age, right? X is the age, is whether that guy passed through 8 of 80, X or 90. So the life table is those ideas. But I don't see, I mean, there's no difference between using F or S or P, they're the same thing. When you talk about discrete cases, like easily transfer from one to the other. Okay. And based on the P, okay, and we can define two important thing is the expectation, right? This is different, no different from what we learned topic 1, right? Just like you repeat the experiment many times in your head, if you know the P, right, then by definition, then you will actually see the relative frequency that X appear is just based on the P, right? So suppose the idea is like toss a coin of 0 and 1, right? Represent number of head, right? And you have half of the time you have the head, half the time the tail, right? So suppose you have 1 million toes, right? Half million will head, half million will be 1. So how many tail, right? That means that if you record it as a random variable, if half a million is 1, half a million is 0, an average of these observations, you consider them data set, then we actually give you half, right? So that is the idea of the mean, right? What we call expectation. And that's how you calculate, right? So the weighted average, right? And a similar idea goes to the variance, right? It's asking the same idea. If you repeat this many, many times in your mind based on the P, then you calculate the average, you can calculate also the variance, right? And knowing the mean and variance for a random variable, okay, actually is giving you the idea of making decision, right? The reason is when you learn from topic 1, looking at the mean and variance is looking at the historical data, right? The mean and variance telling you that mean is summarizing the data, variance is looking at how good are the mean and look how good are the mean, right? So it's looking at the historical data. It doesn't tell you anything about the future, right? It's no use for the decision making here, right? Because we are business decision, we're looking at the future, right? And in that case, what we mean by mean and variance for a random variable is in the sense that if you look at the future, right? We don't know, but mean is looking at the case if look at the future, and mean is the something we expect to be, right? In the middle of what we expect to be, okay? Half of the chance is higher than that, half a chance lower than that, and mean is exactly in the middle, okay? In the sense that if there is a, what we call, right? There's a famous term, we call it a parallel universe, right? If the parallel universe, the expectation is exactly the mean of all the universe, okay? And variance is how it vary among different parallel universe. Okay, I hope this is a clear idea what we are doing, because we are looking at the past, and the past data give us a glimpse of what would happen in the future, right? That is the idea behind when we talk about the return for the stock, right? We have a mean and variance, right, for 2 different stock, right? And that look at historical data, okay, and that will give us a guess of what will happen in the future, and that makes you drive you how you make a decision, right? How riskiness you want, how much greedy you want, right? How much return you want, right? How much a risk you're taking. Okay, so that is the idea behind of why we learn this and how the topic 1, the idea fit into here. Okay, so that's to distinguish the mean and variance in topic 1 and mean and variance of random variable. Okay, they're closely related concept, but they really separate in principle, right? One is look at historical data, want to try to look at what happened in the future. Okay. And we talked about this last class, right? Last week is there are four, I mean, except the first one is four different types of common you observe discrete distribution. I mean, in actually just the main thing is just three, right? So basically, you have binomial, you have Poisson, you have hypergeometric, right? Binomial is asking the case if you consider the world into either two type of outcome, success or failure, right? There may be the outcome, the sample space is very complicated, but you don't want to bother with it, just consider there's a dichotomous classification, success or failure. In that case, binomial is the way you do the calculation. It's always usually the case. A lot of time you do that, right? And some of you actually asked me after the class saying, oh, what happened if you have more than two outcomes we care? Yeah, you do have a what we call multinomial and more than two outcomes. So you can see bi is just a Q, right? Nominal, right? Nominal, binomial. And that would be you can easily check out from the web. That is not or check the textbook. It's not something complicated. It's very similar to what we have right now, but that is beyond the scope of our class. So I think it's okay to check this. It's okay for this one, right? And for the Poisson is a very useful way when we talk about number of events within period of time, right? We talk about how many customers are coming in, how many complaints student would have, right? So on and so forth, right? Though that is something we used to do, right? Counting number 1, 2, 3, 4, 5 is a natural number. If that is a natural thing for the thing you concern, that is Poisson, right? And hypergeometric is very closely related to binomial, right? Binomial can be considered as, and in one application is like you are sampling with replacement, right? And hypergeometric is like sampling without replacement, okay? And that is why hypergeometric is good for you doing audit, right? Many of you are from professional accountancy, right? Hypergeometric is the best we talk about auditing, quality control, right? If you do marketing, quality control, or surveying, hypergeometric is the one you'll be using. And we do note that when you have the sample space is very large, right? You just draw a very small sample of it. The difference between hypergeometric and binomial is minimal. Okay, so you don't need to worry too much about that, right? And probably we'll argue later too is binomial itself can be approximated by bell curve. Okay, so basically you can think that, I mean, also Poisson, when the mean is large, can also bell curve would be fitting in very well. So in some sense, what we are saying is, although that discrete in is important, when the sample size get larger, then the bell curves idea would actually work very well as approximation. Okay, but when in some application where this approximation doesn't work very well, then you have to go back to the discrete case. Okay, I hope I convinced you why we need to focus on this is because look at the audit application, you are not really going to do a very large sample, right? Because you're doing under the time constraint. So you actually have to use the thing that is correct, right? When you make the decision. But I don't think we have time to go over all this thing. So, but just let you know what's going on there. Okay. And you can see there are a lot of things to talk about because there's a lot of information here. Probably you would be wondering what are the stuff you want to memorize. And if you want to memorize, the best thing is not to memorize the formula. That is not really useful for the purpose of learning. Rather, you just probably you focus on the usage. I mean, that's something you want to focus on when you want to use which application. Okay, what distribution is the best? Okay, so when we talk about binomial is a repeating n independent trials. That's something you need to remember, and that's it. The rest, just all the formula, right, is not really really useful. I mean, because you can check it. The best thing if you want to be practical, I mean, you just need to know what this distribution is going to do, right? Just like the Poisson is looking at how many events that happen over a period of time. Okay, number of earthquake, number of customer arriving period of time. Then this is the thing you should remember, because there are too many technical details to keep in your mind. Okay, and it's open book exam, it's open book test, it's open book assignment, right? So there's no need to remember the formula. Okay, except you really have nothing to do, right? Otherwise, the formula is not super important. Okay, and hypergeometric, right? It's just like you do it. Applications, audit, quality control, right? And these are the things that you remember, right? Except formula is not super important because calculator do all those things, right? It's not really useful to remember the formula, but rather you understand the notation and how they do. Okay, and even this formula is not really needed if you really memorize, right? Just they're useful for the calculation. Okay, but not really useful for application, right? Because calculator can't really do it. Okay. Now we today we talk about continuous random variable. Okay, so just a reminder of how we describe a continuous random variable. Okay, and the main key thing to remember here is just this one. Okay, the rest you can safely ignore it. Okay, well, of course you can always check it from your slide, but this is the thing we care. The big F, right, is what is you give me the small x, right, a number, and that is giving you back what's the probability that the random variable less than or equal to that value. And that's the only key that you need to remember here. Okay, and the rest is I have mentioned. Okay, it's actually a mathematical way to write things that you really don't care that much. Okay, and if you really care, this idea of small f, okay, is just same as the p, the rho paid by p, when you have discrete. Okay, the same as the small p, sorry, the big P, and it's just the idea of the bar chart, right? This f, right? It just usually looks like this shape. Okay, this f. Okay, and if you pick up some value, right, from A to B, okay, look at this, the bar chart, right? Look at this area. Okay, this area will be the probability that x is between A and B, right? This area, okay, under the curve small f. Okay, this f here, this is just the probability between x is between A and B, right? The small f. Okay, and this, when you look at the big F, this is exactly B minus A. Okay, so I think if you don't want to know the math, the red one I have shown in this one is the thing you need to remember, and that's all. And that's the thing we need to know. Okay, if you want to map it to this one, it's just like this one, right? It's just you spec F, it's just you sum from A and B, right? Something like here, and right, this is F of B, F of A. Okay, the height, right, is same as this area. Okay, and I'm not going to talk about why this is the case. If you learn calculus, you know why they are the big F and small f, how they relate to each other. and I don't think I want to go about that. Okay. In your mind, if you don't want no calculus, F is just is very similar to the rule played by the big P in a discrete. Okay. And you need to know, just know the idea of what we have written here, right? And don't worry, we'll be doing all this for the rest of the semester. So you will be able to understand. Okay, that's not something terribly deep here. Okay, and you know it, then probably you forgot the definition already. But I hope, is there no problem? Is there any problem? Is there a question? Is there a question on this one? Okay. If no, just before we say goodbye to this slide, okay. So just to all the time when we talk about the bell curve, it's like this, right? When I talk about bell curve, it's actually talking about the small f, okay? Because looking about the area under it, it's just like underneath is the area, the probability, right? So when you look at this, it will look like something like this. Big F look like something like this. Okay, so it's the bell curve looks like in the F. Okay, so just that you know the bell, when bell is look like this shape, the F look like the S shape. It's like, I don't know, it's like it twists the S, something like that. Okay, just that you know what the F looks like. Okay, and this F is the one that we keep using all the time, and you'll be looking at the tables using Excel to do all the calculation. So the big F is the thing that actually we'll be working on using the computer or the tables, okay? And we often use F to illustrate how to do probability, okay? Is that clear? Because F is just looking at the area on the left-hand side. So suppose you have area, if F is this guy, so A is here, go back to this one, okay? This is F of A, okay? This is simply just mean this A is here, all the area on the left, okay? The area is F of A, okay? So that is the thing we'll be using for the rest of the course. So don't worry, you must know it. I mean, if you will know it anyway, okay? You will be using it so often, you will forget about this thing. I mean, it becomes so natural to you, okay? This thing, so don't worry. Okay, I just preview what's going on there. So don't worry about it. You'll be doing it today several times again. Okay. So a final remark here is for continuous random variable, the probability that the random variable equal to a particular value is equal to 0. Okay, because it's so many value it can be, a particular value is going to 0. Okay, and it says 0. Okay, doesn't mean it's impossible. Okay, it's still possible, but just like in terms of measurement, we can't really measure it. Okay, just like if you use the ruler to measure the size of the germs or size of the atom, you cannot measure anything, right? Because the ruler you're going to use is going to be not small enough to detect those things. Okay, so that's why when we look at the probabilities from 0 to 1, okay. So when we try to look at the probability for a continuous random variable, the ruler is too big, okay, to measure the probability there. Okay, so that's why it becomes 0. It doesn't mean it never realize. You can realize, but it's so rare that almost like 0 is a good way to describe what is going on. Is that clear? Okay. Okay, just like metaphor, like a TV show, right? A boy and a girl fall in love and suddenly they break up, right? And the girl don't look at the guy anymore, right? The guy just like disappear from the girl's eye, right? But it's not doesn't like this. That the boy is not going to the Mars, going to a third dimension, right? It's just like doesn't disappear in her eye, right? The same idea here. It's like look at probability, right? When you try to measure from 0 to 1, you can't really find it. It's too small. Okay, it just so you can't see it. It's 0. Okay, And just because it's 0, so all these 4 are the same thing. Okay, just to make sure that just emphasize they're the same thing when continuous. Okay, when discrete they are very different, but continuous the same. Okay. I hope this make it clear what's going on. Now, is that okay? If okay, then we talk about expectation and variance. Okay. And although I look at here, I have integration from something crazy to something crazy. I mean, the idea is same as we have before. It's just if you try to repeat this experiment many times, you got all the observations, you calculate the mean, this expectation. Okay. And variance, the same idea, right? You have many observations, right? And then you have each observation, you minus the mean and take the square and do the average, then you get the variance. The interpretation is the same, okay? But because we're talking about continuous, we cannot use the idea of summing, right? Because remember how we have discrete is like this one, right? Summing x of px, right? But when you have integration, you have to add something where we are thing to go with it, right? So this is the where we are thing go with it, right? Okay. So and if you're math serious, then you actually know this guy is exactly P. Okay, because this is exactly what it means here. Okay. This is D of x. This is f of x. So exactly dx is the width and fx is the height. So that's why exactly the bar of this f graph, this area. Huh? No. Maybe the other guy. Okay. So that is the expectation. Okay. And the variance. Okay. Basically, just to remind again, this is no different from the discrete case. Okay. You just repeat this many times, and that gives you the mean and variance. Okay. You repeat many times, the average or the observation gives you the mean. That's expectation. You every observation subtract the mean and take square and calculate the mean again of this object, then you get the variance. Okay. Same as what you learned from discrete. All this is clear what's going on, although the math look crazy, and because we have to put definition here, right? Otherwise you don't know what's going on. But we're not using this integration anything for our class. Okay, so don't worry about seeing this, but just same as the discrete version. Okay. So is there any question? I mean, any question? Okay. Now, for here we will be giving you almost everything we use in our class. Okay. I think everyone, probably most of you would know the normal, which is the bell curve, right? This is the bell curve. It's normal. Something we will talk about that soon, today. And these are all related to bell curve. Okay. So basically, the bell is all bell. Okay. And we'll talk about, hopefully we can talk about today. If not, then we will left some of them for the next week. Okay, probably next week we will finish, at least finish half of it. And you ask what the uniform and what the exponential. Okay, I think uniform is rather not difficult to see what the uniform is. It's like equally likely. Okay, what it looks like, you try to plot the f, later you will see. Uniform, we try to plot the f. Okay, it's like a flat curve. It's a flat one, which means that any value is possible, right? Equally likely, right? Say suppose you look at from A to B, okay? The probability, right, is given by this area, right? And if you look at the other case, we'll talk about it in more detail, but I just give you a preview here. C and D, right, is this area, okay? And because they're the same height, if A minus B, B minus A is equal to D minus C, the same width, the same probability, right? So it's like every equal distance, right, will give you the same probability, okay? So that's uniform. Is like everything is possible in equal likelihood. So it's the simplest thing you can imagine, right? And probably you ask when you would use this, right? And the natural question would be, say, you don't have idea usually, okay? So say suppose when someone say, okay, you go to the TV, then say, okay, what's today Hansen index? I don't know, maybe 17,000, I don't know, or 18,000. And usually you watch the TV, and the expert will say, okay, I expect today will be between 16,000 to 18,000, right? And what does it exactly mean? If that guy doesn't say anything about what the median, what the mean, what it looks like is not normal, then you assume uniform, right? It's like anything in between is likely, right? We don't specify usually what we mean by uniform, right? You start from uniform is the best one, okay? And probably we don't mention in our class, right? But this is usually uniform is a good way to start when you have a AI or Bayesian learning process, right? You start from things, okay? You start from uniform, right, to guess. And then based on the information update, you just keep refining your base using the base rule to refine. Then at the end, you get something out, right? So that is usually that how modern AI machine learning being done. You start with a uniform distribution, you keep base updating, you come up with something nice form, then you know what to do, right? So that is how things being done, right? Just like I think someone would notice probably an application would be something like this, right? I don't know whether you guys are too young, but AI can train how computer play games, right? And one of the oldest game is called Space Invader. I don't know if anyone knows this game. Maybe you guys are too young, but it's a very old game where there are many aliens are here. Okay, many aliens are here. They're moving downward, right? You are protecting the Earth, right? You have your plane, okay? You're going to hit some alien. If you cannot kill all the alien, then you die, okay? And then how you would, if you try to build an AI to train the plane how to play, right? How are you going to do, right? You're going to use a uniform distribution, right? You're going to hit uniformly here, right? And see whether how you win the game, right? And then you just change the strategy based on where you can hit more, right? And then keep update, right? And keep improving, and then come up with very smart AI to do things, right? So that uniform, this is the thing you start, right? So uniform is something not usually you do, but this is the thing that you don't know, and how you start is start from uniform, okay? And second, we talk about exponential, okay? Exponential is closely related to Poisson remain in the discrete, okay? The Poisson, remember what we said is you will have a time interval, right? And you cut the time interval into very small interval, very small interval, right? And each small interval is actually a binomial trial with probability P, right? And there's an event happen in that one small interval, right? And Poisson is asking how many events can happen in this interval, right? That's a random variable, right? Let's care how many events happen in this interval, okay? Then exponential is asking the following question. It's asking, suppose there's a one event here, okay? One event here. Exponential asking, what's the time to have the first event happen? Okay, let me repeat. When we expect the first event will happen. It's called exponential. Okay, we'll do it. We'll talk about it more in detail, but it's just like when first event will happen, that is exponential. So that's why we'll use it to model when things happen, time until things happen, right? It's very useful, right? You want to model when earthquake will happen, when disaster arrive, right? Or when will our next customer arrive, right? Time will they arrive, then it's a exponential. So basically it's time, right? The time, modeling time, right? And Poisson is modeling a number of things happen in a period of time. Exponential is time for the first arrival, okay? And I guess I don't need to motivate why we talk about normal, because almost everything you can put in normal if you don't really sure what to do, right? Because normal is so common, right? I guess it's clear what we're doing for the roadmap, okay? So we go one by one, and hopefully we finish at least half of it today, or more than half. I mean, at least hopefully come to the normal. Any question? I hope you know what we're doing, okay? And we probably use all these things for the rest of our course, okay? So for all our class, don't go away with this, okay? Basically, our rest of class will be talking about binomial and normal, chi-square and student T and F, okay? Exponential, we'll use it like Poisson. We just talk about this for this topic. For the rest, we forget about it, okay? We no longer go back to Poisson or exponential, okay? We focus on normal for the rest of the class, and student T and F, and also the binomial. Is that clear? Okay. If no question, we'll go ahead to talk about uniform. Okay. Again, there's a lot of formula here. Okay. They are not super important. Okay. But the idea is trying to give you what's going on. Okay. And give you some idea. Let me draw a diagram here. What is uniform? Okay, uniform A to B here, okay, is the following. Okay, A and B, we draw F, okay. It's just a flat thing, not flat enough, right? Just straight line. Okay. And the next thing we want to say is what is the height of this? Okay. The height of this is just exactly B minus A here. Okay. You ask why is the case? Because the area, okay, the area in this curve, area under this big F, okay, should be 1, right? Because the area under this F curve is probability. Okay. So this is B minus A, right? So the width times the height must be 1. Okay, the width is B minus A, the height must be 1 over B minus A, and type and multiply them is 1. Okay, so that's why in the slide you will see, right, X is 1 over B minus A is the reason. Okay, because multiply must be 1. Okay, and now what is it looks like when you have uniform? It will look like this. A and B, okay, a big F, okay. You look like this. When less than A is always 0. When more than B is 1. Okay. And if you learn integration, you look at this. Oops, sorry. I think I should use a straight line here. Okay, so it's a straight line. Okay. Well, you ask whether you need to know this graph. No, you don't need to know. Okay, I just demonstrate what is F and big F and small f here. Okay, I don't expect you to how to draw it. No, I don't need to do that. Okay, what I need is just, okay, this is how you have how the F and big F looks like. Okay, Okay, you need to know the normal, okay, the bell curve, but this is the thing that looks like. Okay, and and we got the straight line here, right? So this is 1, right? So each point of x here, right, is coming from x here, right? This is f of x, the height, right? So what is f of x? Okay, so use the idea of similar triangle, right? So similar triangle is the height of the smaller one. Okay, maybe you say green color. This is a smaller triangle here. Okay, and this is the bigger triangle here. Okay, and because they're similar triangle, right? So I can look at the height comparison, which is fx over 1. Okay, maybe I use another color. This is fx, right? And right, so be equal to what? Look at the small triangle. The lower the bottom, right, is x minus a, right? And look at this purple one is b minus a. Okay, so that's why in your slide fx is x minus a over b minus a. Okay, again I would want to emphasize it. I'm not asking to derive it. I'm just telling you what is a small f and big F here, trying to give the idea. Okay, I mean you would not memorize anyway, but I'm just trying to show you how do you get f and big F, small f and big F in this case. Okay, I hope this is convince you what we are doing is the right thing. Okay. Okay, as I said, it's not important. Okay, I'm just telling you that using a uniform as an idea, okay, what it looks like. Okay, and remember uniform, as I said at the beginning, it's just saying that when a uniform between A and B is like any number between A and B is possible, right? Equally likely. Okay, between any also A and B is not possible, between A and B is possible. Okay, you don't have any idea which point is more likely than the other one. Okay, that you use uniform. The simplest you can imagine, right? Okay, and this looks like the small f and big F look like this. Okay, and is that okay? I mean, as I said, I'm not expecting you to know how to draw it, how to derive it. There's no. Okay, just trying to explain what you see in the slide. Okay, and as I said, it's not important. Okay, so that's why I didn't expect you to memorize anything. Okay, so just to explain this is the case. Okay, is that the important thing is equally likely between the relevant range is A and B. Okay, and here we have mean and variance. You can see I don't expect you to remember as well. Okay, but just the formula here. Mean, I think is you probably would expect this is the true. The mean will just the middle between A and B, right? A and B is the range between A and B. The mean will be just middle of A and B. Okay, and that is it. And the variance will be just the difference squared divided by 12. And probably you will ask 12 is a very real thing. Yes, it's a very real thing. We're not going to prove it, and you won't use it anyway. Okay, I put it here because we talk about mean and variance for discrete. Why don't we talk about the same for the continuous? Okay, here most likely just demonstrate what it is, F and big F. Okay, not going to do anything. I mean, probably you never use it anyway. Okay, just to demonstrate the idea of small f and big F. Okay, is there any question? If no, then this is the A and B is between 2 and 3. It will be this one because the base is 1, so the height must be 1. So here the base is 4, the height is 1/4. Okay, so that is what it supposed looks like. Okay, and here is the formula probably you apply, right? So the question would be, someone told you that the Rainfall is uniform between 1 mm to 4 mm. What is expected rainfall and the variance? Oh, so there should be a space here. Okay. And just apply the formula here, right? Here it's just like A is 1, right? For B is 4, right? A is 4, right? So A is 1, B is 4, right? So this is just A plus B over 2, right? This is B minus A square over 12. So that's it, okay? I just need you to know how to apply it, right? Is that clear? Is that okay? I probably just too trivial, but just plugging in the numbers. Okay. You just here just like the rainfall between 1 and 4 is equally likely. So you cannot tell which one is more likely. Okay. And I guess the other one is something we would care a little bit more. Okay. This one, okay, is asking the probability between 1 and 3. Okay. So this question is like this one, right? Asking this question. Indeed, they're asking this one, right? Probability between 1 and 3. Okay. Yeah, just write it back there. After this, we have a break. Okay. So you're asking this one. Okay. But there's nothing lower than 1, so they're the same. Okay, because it's always between 1 and 4. So, and this guy is exactly f of 3. Okay. That's how you get this formula here. So I think I sum a little bit here, but I think it's clear what's going on. Okay. Or the other way around is you can think about this guy is just f of 3 minus f of 1. Okay. In that case, f of 1 is actually 0. Okay. So you also get the same idea. Right? Because it's always between 1 and 3, 1 and 4, less than 1 is 0. Right? So if you still do not fully absorb, so let's go back to here. Okay, this x is between 1 and 4, right? And this is the f, okay? And uniform means the height, right? And what is this guy? Okay. In this guy, the height is simply the distance is 3 here, so this is 1/3. Right? This is 1/3. So I do this is 1/3. Why? Because this is 3. Okay. 3 times 1/3 is 1, right? Because this area must be 1. Now, probably the question is, what is between 1 and 3, right? So 3 is here. It's asking this area, right? This is probability mean, okay? Probability between 1 and 3 is the area under F between 1 to 3, right? So then it's simply looking at your primary school, right? This is only 2, and this is 1/3. 1/3 times 2 is 2/3, right? Is that clear? So that's how you get the same answer using an F, big F, or using a small f also fine. Okay, just illustrate how you can get it. Okay, and of course, you just apply formula anyway. So I hope that will be clear. Okay, and I guess some of you might have questions. I think it's good to have a break before we go ahead to our topic exponential. In the meantime, I'll go around to see if any question. Okay. So let's resume at 5:30. Okay, I just go around. Give me 10 minutes, 5:32. So go around to see if any question. Hi. Hi. I guess we can resume. So actually someone asked you during the break. I think it's a good question as well. They asked me if I change from 1 to 2, okay, what would be the answer, right? So in that case, what we have is probability that 2 to 3, right? You'll be doing this, right? Probability x less than 3 minus probability x less than 2, right? So which is f of 3 minus f of 2, okay? F of 3, you already have here, right? This is how to calculate this, right? And you would follow the same procedure to do f of 2, right? So f of 2 would be just 2 minus 1 over 4 minus 1, right? Or in that case, if you don't like, you can directly see from this graph here, if 2 to 3, it's just like here, the blue one, right? From 2 to 3, the width is just 1, the height is just 1/3, so it's actually just 1/3. Okay. So if you try to do that, okay, is that okay? I hope it is clear what's going on, but don't worry, in the assignment you'll be doing something similar, so you will be able to understand what's going on. Is that okay? So the more question you're asking, the more thing I can explain, so you would know more. So I encourage you to ask questions whenever you feel free to ask it, right? Any more question? If no, then we continue. Is there a question? No, then we continue. So we skip the proof part in case you want to know this result. I think the proof, all the steps are pretty straightforward. I mean, although some of you told me there's not that straightforward, but if you really don't know, just ask me. Or in the textbook already have explained all the every single step, but if you don't know, just ask me. Okay, it's not a big concern. Okay. So here, what we have is called exponential. Okay, and as what is this actually is modeling. Okay, the application is modeling time until something happened. Okay, and one thing important is the term called memoryless. Okay, if we have an event, okay, we try to model time until something happened. If it has no memory, okay, then exponential is the only way you can do it. Is the best way to do it. Okay, that's the only way. And what do you mean by memoryless? Okay, memoryless means it doesn't matter how long you wait. Okay, if it hadn't happened, doesn't really change the probability. Just like if you try to say, okay, I'm waiting for someone to come in. Okay, and what's the probability that someone come in say next 10 minutes? Okay, now suppose I wait 5 minutes already. Okay, I ask, okay, what is the probability that next 10 minutes someone will come? Okay, do my answer for the first question and the second question the same? No, there's no difference. Regardless of how long I wait, the answer is the same. That's called memoryless. Okay, let me repeat the statement. Okay, I'm asking the question myself. What is, say, next 10 minutes someone comes in? Okay, and now I suppose I wait half an hour. I ask the same question. Okay, does it change? If not, that's not it's memoryless. Okay, there's no memory of the process. So the time passed has no meaning. It's just like the same thing would happen, right? That's called, then in that case, it's exponential. Okay, it's not in a lot of cases that's true, right? If you would imagine if there's no earthquake for today and tomorrow, then it should be the same probability, right? But sometimes a lot of things is not memoryless, right? Suppose you are going to make an appointment with your friend to meet in Mongkok, like at 8, right? So you arrived early, right? Maybe you arrive at 7:30, right? If you think your friend is punctual, right? It's very likely that he's arriving before 8, right? But if you until 8 he's not coming, she's not coming, then you might think that he should be coming very likely in the next half an hour, right? But in the worst case scenario, he's not still coming after 8:30. Okay, you would think he should be very likely to come, right? So in that case, that is not memoryless. Okay, then you is likely to be different, right? It's the memory, and a lot of time memoryless is a good one, right? We talk about number of customer arrive, it's a good thing. Earthquake, tornado, that is fine, right? You think independence is a good assumption, then it would be a good one. Okay. So here is what is the value you can put, right? Time until things happen, right? It may not happen in a finite time, so it's just sum from zero, starting from 0 to infinity. Okay, any number is fine. Okay, start from 0 cannot be negative, right? So time until something happens cannot be negative. Okay, and you will see this kind of funny thing. Okay, and if you look at this expression, looks really crazy, but actually it is something that you might have learned before. Exponential look like this kind of shape. Okay, it's like something, I don't know, you ski down the mountain. Okay, and that is exactly the exponential mean, because it drops like an exponential graph. Okay, and if you learn physics, this is what happened when we talk about the radioactive thing, right? This exponential decay, right? And here you can see this E thing here. E again is the natural number 2.713. Okay, and the question you're asking probably what is the lambda means. Okay, what is the lambda means? Okay, what's the lambda mean here? Okay, and later you will see, as we don't prove, but lambda actually, the inverse of lambda, okay, is the expected time that thing will happen. Okay, so suppose you expect this event will happen in the next 10 minutes. Okay, lambda will be 1/10. Okay, okay, so is that clear what's going on? Okay, lambda is just the inverse of the mean. Okay, okay, that's why in some textbook they would do the following, which I think sometimes can be rather confusing to you if you read the textbook, some of the textbook, not mine, but they would use theta here, means the theta, and this one they will write 1/theta E negative x 1/theta. Okay. This is some textbook they will use. Okay, but they're the same thing. Okay, because you call theta is 1 minus lambda, the same thing. Okay, and they're the same. I mean, it depends on whether you like theta or you like lambda. Okay, is that clear what's going on here? Okay, so just to repeat what's going on is you have something going to happen. Okay, and it doesn't matter how long you wait. If it doesn't happen, the same thing would goes on. Okay, basically you don't have a clock with you. If it doesn't happen, you look again, make your guess, the same thing will happen. Okay, and what is the mean thing that happened is called 1/lambda. Okay, and if this is the case, then it just look like this curve. Okay, and if you again remember, okay, here I have lambda is 0.2, right, which is 1/5. Okay, and this is 1/2, right? So for the red one, okay, the mean, right, is just 5, right? And Let me use the blue color to distinguish them. All right. For the blue one, what's the mean of the blue one? Right. This is 1/2. Just 2. Okay. So just imagine that for the blue one, right, means that you use the units like 2 minutes. After 2 minutes, things will happen, or 2 hours, things will happen. Okay. So that's why the graph is much higher, right? Because it's likely that it's 2, right? 2 is here, right? So we're likely that before 2 things would happen, right? And red is also the same. Red is here, right? Red is 5, mean is here. So it's less likely that it's happened before, right? So that is what this graph looks like. Okay. How it looks doesn't really important, but this is what we call the exponential curve. You learn in the high school, right? This is what it looks like. Okay. I mean, you don't need to memorize the graph. I mean, it's not really important. Okay. So just to remember from this graph, you know, the blue curve is faster than the red one. Okay. The faster is more like it just shift everything to the to this side, right? Just shift up everything, right? The slope is more steep, right? Because likely to happen before than after, right? The smaller the lambda, the more likely that happen earlier, right? The curve is more steep. So, and if you learn calculus, which we don't do it, but the big F, it's coming from this formula, okay, which is rather simple, right? Just like 1 minus e to the lambda x is the probability that things will happen before that time. Okay. And another formula, the variance is lambda 1 over lambda square, right? So that is the only thing. Probably for exponential, what you need to use most of the time is just the thing I have circled, this guy, and this guy. Okay. And that's the thing we need to use for calculation. Okay. Let's look at the example if there's no question. Okay. Let's look at example, then you will appreciate what we are doing. Okay. And as I said, the exponential is modeling the time until things happen. So it's very useful. Okay. So here I have a question. Is the time for next customer to arrive follow exponential? Okay, with mean 20 minutes. Okay. And remember what's the mean? Mean is 1 over lambda. Okay. So we say with 20. Okay. So this implies lambda is 1 over 20. Okay. That is exactly here what I have written down above. Okay. So now the question is asking is, okay, this is what we know. And probably ask again, how we get 20 minutes. This is coming from historical data. Okay. Look at data. When customer comes in, okay, what's the mean of that? The mean is 20 minutes. Then that's the data, right? Because you can calculate each day what's the interval between one customer and the other, right? If 20 minutes on average, that is what it is, right? And if you believe that no matter how long you wait, okay, the probability that the customer arrival remain the same, then it's exponential, right? If you believe there's a time for things happen is have no memory, then that's a good thing. That is the used to exponential. Okay. Here the question is, what is the probability that arrive in next 10 minutes? Okay. So, which asking that is the probability that is the random variable that less than or equal to 10. Okay. And do note that I didn't very specific about whether it's less than or equal to. Okay. Although within, I think in English means this guy. Okay. But doesn't really matter anyway, because when you have a continuous, they're the same thing. Okay. So I don't need to be very strict about this particular point. Okay. So this is less than this, right? Just like f of 10, right? Of course, if you are really strict, actually we're talking about which is 0, x, and 10, right? But this is just f of 10 minus f of 0, and f of 0 is just 0. Okay, so really not really a big concern for us, right? Because nothing below 0, so we can basically use this one. And the formula is 1 minus e negative lambda x, okay? And lambda is 1 over 20, and x is 10, so give you the probability like 40%. Okay? So it's rather surprising, I would say, this result, right? Because the average is 20 minutes, okay? And you mean average in the middle, right, already? But you will see most customer actually arrive within 10 minutes, right? Half of the time, right? 4.4, right? And you would little bit say, oh, it's interesting, right? Because I would say it's a little bit fun, right? Because by exponential, it means most actually a lot of people actually arrive way before the mean, right? Actually, it's not very surprising because this is very skewed distribution, right? Because look at the exponential, a lot of the probability is on the left-hand side of the mean, right? Because exponential decay. So that's why, although it's 20 minutes, actually a lot of people actually arrive in the first 10 minutes. Okay. I hope that is clear what's going on. Is that okay? Is that a question? No? Okay. Good. So this is the next question. Okay. That I think is not very difficult. The same process, but instead ask next 5 to 15 minutes. Okay. So directly you will see what it's asking is this one, right? Between 15 and 5. And immediately you know this going on is like this guy, right? Just the graph, if you try to look at it, is x is between 5 to 15, right? This is the curve here. Okay. And we are talking about this area, right? The purple area is what we want. And how do we do that? We're going to use the blue one, which is F15 is this guy. Okay, this is F15. Okay. And subtract it from, I guess I use green. The green one is the horizontal one, right? The blue horizontal minus vertical green is equal to the snake area purple, right? Maybe I erase this one. I use the purple, right? I think that's easier to see. Okay, I hope this is more clear what's going on here, and just put the formula there. Okay. Is that clear how we do it? Okay, I'm not going to go to step by step. I think it's very too tedious to go by that because you're already a college student, right? I'm not going to go one by one like the primary school. Is that okay? Any question? Okay. Now, if that is okay to you, Then we are lucky we can go to talk about the bell curve. Okay, I think it's good to have something concrete because we'll use it for the rest of our course. Okay, you'll be using it all the time. And you probably ask, okay, the bell curve is, you know, if you learn anything from the high school, you learn a bell curve is the most common one. Okay, you look at all the data, look at the IQ, look at the weight, look at the height, look at many things. Bell curve is the thing that you often observe. Okay, probably you would ask why. Okay, we don't prove it. We'll mention a little bit in the topic 5, what we call central limit theorem. Let me write down. Central limit theorem. Okay, and probably you can say for statistics, this is one of the single most important theorem that you should know and you should remember. And if you look at advanced probability class, they probably spend the whole class to do this. Okay, not whole class, whole course to do it. Okay, and what it's supposed to say is, if you look at things that is determined by many factors, okay, then end up you will see a bell curve. What do you mean by that? What is IQ? IQ is determined by a lot of things. Your gene coming from your dad, your mom gene, right? Your dad and mom, it depends on your grandfather's, grandmother's genes. Also depend on the environment. Also depend on what you eat. Also depend on what you learn in the kindergarten, so on and so forth, right? You determine many things. Then you will have central limit theorem bell curve. And your height, your weight also the same, right? Your weight will depend on what you eat, what you drink, whether you do exercise, okay? The genetic thing, the height, everything will be, when you measure, then it's normal, right? So because in the real world, it's very hard to find things that is not determined by manual stuff, right? So many things is determining something, right? So normal or bell curve is normal, okay? That's why I call normal, okay? It's very normal to see, right? If it's normal, it's normal, right? So to look at the bell curve is normal, is like this, right? Normal, okay? Is saying that this x can be any value from negative infinity to positive infinity. Okay, there's no limit to what number you can take. At the yellow line, a bell curve. Okay, that's why this is got this small f here, right? Small f. Okay, and big F it look like this. Something like this again. This big F. Okay, this is small f. Okay, so when I talk about the bell, it's actually this guy. Okay, this is the bell shape. Okay, and this is symmetric, right? This symmetric, maybe. Maybe I would say symmetric. Line here, okay, symmetric, okay, and this is symmetric. There's a mean, the highest point actually the mean. Okay, this highest point expected x is called the mu. Okay, and it's symmetric about mu. Okay, the important thing is symmetric about mu. Okay, is the special property of this bell curve. Okay, and the variance is called sigma square. Okay, okay, and because symmetric about mu and symmetric about the mean, so that means the skew is 0. Okay, And actually this kurtosis or excess kurtosis will be 0. Or kurtosis is 3, so the excess kurtosis is 0, right? Excess kurt is 0. So this is what you need to know for the normal. Okay, normal. There's only 2 things. Determine what it looks like. One is the location of the hue, okay, which is the mu, and on the 2 sides of the hue, okay, so the peak, it is symmetric, okay, and how tall is this mountain is determined by sigma, or how flat of the 2 sides, right, is determined by sigma square. Do note that, remember, right, the area under this F is always 1, right? So that's why by changing the sigma, then just like pushing the peak of the hill, right? Because the area under is always 1. Is that clear? What we need to know, the normal is basically the bell curve, look like this, like bell, okay? That's what we know. Okay, of course, later we will remember certain things, but this is the graph we need to know, okay? We'll be using this so many times in this semester, so don't worry, you will always remember this. There's no way you can forget about this, okay? If you don't know this, that's my problem, okay? Because we talk about this so many times, okay? You can't forget it. Is that okay? Okay. And probably you may ask what's the formula for F and big F? The answer is, you don't need to remember, is a complicated thing, okay? And you can see we have something complicated like this, okay? And complicated like this, okay? And those who learn calculus, actually, we notice that this one is not integratable. Actually, you can't integrate it. There's no closed form solution, okay? This is what it is. You can't simplify it. You have to, there's no way you can calculate this guy in general, okay? In general, you have used computer to do it, okay? So that's why even though you're good at math, you cannot do anything except use calculator, okay? And as I said, the mean and the variance are denoted by this, okay? And there's nothing more than this one, okay? So basically, you don't need to memorize this one, okay? Okay. The only thing you need to know is this is the support, can be any number, positive, negative. Mean we call mu, variance called sigma square. So there's nothing new there. And education-wise is most commonly you use, especially when what you observe is a combination of things, right? IQ is basically the mean of many things, weight and height and many things, right? It's like that's what it is. Okay. So is there any question? I mean, of course, there's not too many things you need to remember. Okay. Except you know there's a bell curve. Okay. So let's see what the graph looks like when you have different mu and different sigma square. I think it's important because we keep using this all the time, so it's good to know what do the bell mean. Okay. So first, probably you want to compare the case where you have red and you have the green one. Okay. Red and the green one, they share the same mu. Okay. The only thing is the red one has higher variance, higher sigma than the green one. Okay. And as I said, right, the area under the curve is always 1 total area. So if you increase the sigma, which makes more variance, right, that means that you have to push it down like this, right? Just like imagine you have a play doh, right, or dove, you just pump, then you will just become flattened, right? and is symmetric about 0, right? Is that okay? If you have lower sigma, you just push up. If a lower sigma, you just push down. Okay? I hope this is clear. The second one is called compare. You want to compare maybe green and blue. Compare green and blue. They share the same sigma. Okay? Means how they spread out the same. Okay? The difference is the mean mu. The blue one is -4. The green one is 0. So basically, mu is just shifting. Okay? You shift left or right. Okay? Because sigma is same, just like the spread out is similar. Okay? Location of the mountain is determined by the mu. How tall is the mountain is determined by sigma. Is that clear what's going on? Okay? Is that clear? Good. So I think we can talk about this because we keep using this notation. I think it's good to know what we say usually. Sorry. If we say X follow a normal distribution with mean mu and sigma, we write this. X, you can see a snake here. In English is you will call distributed S. Okay, maybe I write a better English because having a little bit too curly. This should be S. Okay, or X is like spread out like a bell curve. So you can say X is following a bell curve. Okay, with the mean mu and sigma square. That's it. Okay, and this notation. Okay, and now I want to this notation. There's nothing new here. I want to talk about this one. Okay, actually you have learned about it as well. Okay, now one first thing is interesting for normal. Okay, actually only true for normal is if a random variable follow normal. Okay, a linear transformation means you multiply certain thing, you add certain thing, it's still normal. Okay, and this is not a general thing holds. Okay, this does not hold in general. Okay, but for the bell curve, it is still hold. Okay, let me repeat the statement. When you multiply a number plus a number, okay, in general, it may be exponential. You multiply some plus something, it need not be exponential. Okay, something like binomial also doesn't have to be the same thing. But for normal, it's good is if you multiply a constant A plus a constant B, it remains a normal. Okay, and when you have normal, okay, this is the new mean. Why? Because expected AX plus B is A expected X plus B, and this is mu. So that's why this is new mean, right? The same idea works here. Variance AX plus B is just A square variance X, right? This is just sigma square. Okay, so this is how you got it. Okay, do note that these two lines would hold regardless whether you call it normal. Okay, what is new thing in this slide is about it's still a normal one. If a bell, you have multiplied something plus something, it's still normal. Okay, that's the only thing. Okay, and the idea is not surprising because you have a bell curve adding B, just move the bell to the other side, right? And you multiply the bell, it's not like making more spread out, right? Multiply it just more spread out, right? Because normal come from negative infinity to positive infinity, right? So multiply it just like making everything expand, move ahead, right? And spread out more, okay? So that's why it's very convenient. Do note that this does not hold true for in general. Only because you're bell, you can do it. Okay? Just like you can consider uniform. Uniform, if you multiply, and plus it's not uniform. Okay? Uniform, this one doesn't, it's not true. Okay? Is that okay? Now, I guess that is the reason why you learn one important thing is what we call standardized normal. Okay? It is because that we can always, no matter what we do, you subtract and division or multiplication, it doesn't change the shape. Okay? So that's why if this is normal, you subtract the mean, okay? What you will get? X minus mu with a normal distribution with mean 0, sigma square. Right? If you try to use what we learned, let B is negative mu. Look at the previous statement. Okay? Here, how we do it, B is equal to negative mu. Okay? Look at your slide. In your slide, this is what you get. Okay? And how you get from here to this one? You said A is 1 over sigma. Okay? Then this is what you get. Okay? Then you get what we call a standardized normal. Is the bell curve, okay, that we will be using. Okay? Basically, what it's doing is no matter which bell curve you're looking at, by doing this normalization, you can always transform to normal CO1, standardized normal. Okay? Probably you would ask why we care about this particular transformation. Okay? You would not need it if you use a modern computer. Okay? You calculate the probability, right? If you give this, I'll give you this one, ask you the probability between X between A and B. Okay? Modern computer quickly give you the answer. Okay, that's no problem. Okay, but if you do not have computer, what can you do? Right? Then if everything can be simplified to this guy, okay, right? Then this, later we'll do it more in the next class, is we will try to transform this guy. Okay, you subtract the mean over sigma. Okay, you do the same operation for this sigma here, A minus mu over sigma. Okay, and this guy become exactly Z. Okay, and you only need to know how to check one cases is not standardized normal. Okay, when you look at the table, you only need to look at one table. Let me repeat the statement why we don't look at this is if, remember, calculate this thing, you cannot use hands, right? You have to look at, okay, for each mu and sigma square, you can have a table, right? What is X is, you have table F, all right? F of this, right? You have X, different F of. So what I mean is you would for this question, right? How can you answer this? Is you need to have a table of x of different value, f of x, right? The cumulative one. You have to have a lot of value, right? And this value have to depend on what is mu and sigma square, right? So you need to keep this table for every mu and sigma square. Okay? But if you allow ourselves to convert everything into 0 and 1, okay? In that case, we don't need to have many tables. We just need only one table, okay? That has mean 0 and mu sigma, you have a sigma is equal to 1, okay? In that case, you only need one table, okay? Let me repeat the statement here, okay? Because this one can't be calculated, right? So you have to calculate what is FB minus FA, okay? And do note that FB minus FA depend on what is the mu and sigma, right? So you have to, if you really want to do it, you have to have every possible mu and every possible sigma. You need to have this table, right? That will, you have to kill many trees to do it, right? But now we say that regardless of this, we can simplify in this form. We'll go more detail later. And that if you everything can simplify to 0 to 1, this only keep one table. Okay? Every calculation, we always from here go to a standardized normal, and we can check this table, then we're done. Okay? That's why we call standardized normal. Okay? So it will be not very clear right now why we do this, but in the next class, we will talk about how to use a set table to do all the things we want. Okay, so it's not very clear why we want to do that, but very soon look at the example. If you're curious, then you will see why we are doing this. Okay, and I guess that's all for today. I will see you next week.